All right, thank you, and welcome to the PhD defense of Salme Cook. Just want to say a few words about Salme. Very brief. She came to UNH in the fall of 2013, previously working as an environmental engineer in both private industry and prior to that for the Army Corps of Engineers in the New Jersey, New York area, as I recall. She got BS and MS degrees from Stevens Institute of Technology. And as you'll see from her talk today, that she's spent a significant amount of time thinking about the Great Bay Estuary, taking field observations and running numerical models, including what you find just outside on the display out here in front of Chase 105, is a model of the Great Bay that comes from her work on a bathymetry model, actually put together by Mike Hitchcock, and with the help of Tom Butkevich has been visualizing that flow up there. And it's actually interactive. If anybody hasn't seen that, you can actually point at it and put little flow vectors in there and see where things go around. Anyway, that was all Salme's work. It's been a pleasure working with Salme over the years. She has developed significant new research directions for my group, but also for UNH and the things that we're approaching now, including the proposals that we're writing. I'd also like to point out she spent significant amount of time playing and thinking about soccer. Many of them against you, sometimes at your own peril. She's significantly good at soccer and actually coached at the high school here at the Oyster River High School for several years. Very well thought of coach from the high school. I won't go into too much more about her athletic prowess, but it's significant as well. Okay, so before I begin, I want to introduce the committee. Diane Foster from Mechanical Engineering, Rob Swift, also from Mechanical Engineering, Jamie Pringle from Earth Sciences, John Kelly from NOAA's National Ocean Service, and also for the Center for Coastal and Ocean Mapping, and Chris Sherwood from the USGS. Also a future colleague of Salme's at the USGS. The format today, Salme is going to talk for 40 or 45 minutes, something like that. Then there'll be questions from the audience. Then when we're done with that, we'll excuse the public and the committee will stay behind and talk to Salme in this room. So without any more, thank you, Salme. It's all yours.
Thanks. All right. Thank you all for being here today. The title of the dissertation is The Effects of Waves, Tides, and Vegetation on the Distribution of Bed Shear Stress in the Great Bay Estuary. But the broad question that I'm trying to address is, does sediment resuspension from mudflats significantly contribute to nutrient loading in estuaries like the Great Bay? And what's the relative importance of waves, tides, and vegetation on the distribution of bed shear stress and then sediment resuspension in these environments? When I first approached Tom 6 or 7 years ago, I was really interested in coupling numerical models with observations and actually learning how to collect observations and how they might feed into numerical models and how numerical models might help us design better field studies. So a good portion of this work will combine these two. Also leaning heavily on lab studies, particularly looking at nutrient loading. But my contribution is mainly in the numerical modeling field. So the outline of this talk, I'll talk about some research motivation, background, and the Great Bay Estuary. A good portion will be spent on the first paper, which is the model setup and validation. Then I'll talk about bed shear stress distribution from that validated model, go into some vegetation and nutrient loading effects, look at the influence of waves, and then go into conclusions. And vegetation influence of waves are papers 2 and 3. And you can follow in the navigation bar on the bottom. But broadly, estuaries are these bodies of water that are affected by fresh water flowing from rivers and mixed with marine ocean water. The mechanisms that drive this mixing are seasonal and event rain-driven freshwater flows from rivers. And on the ocean side, you have the effects of tides, atmospheric low and high pressure system, and waves. The things that we're interested in that are mixing are salts, temperature, sediment, nutrients, and pollutants. And we look at advection, diffusion, and turbulence as mixing processes. The reason why estuaries are so important, 22 of the 32 largest cities in the world are located on estuaries. 14% of the coastal communities in the United States actually produce 45% of the GDP. And 76% of trade involves some sort of marine transportation. And coastal recreation brings in about $8 to $12 billion a year, although I imagine that number is only increasing. There are some services that estuaries provide that aren't monetized, and those are called ecosystem services. So estuaries are often called the nursery of the sea. They provide really important habitats for shorebirds, fish, oysters, crabs, and lobsters. Other services they provide are wetlands on the fringes, provide shore stabilization. They regulate floods, decrease the effects of storm surge. That was really important in Superstorm Sandy on the New Jersey coast. They also act as buffers. They act as a sediment trap. They remove nutrients, sediment, and pollutants from the water column. They're important in that they have high primary productivity. They're important in carbon sequestration and nutrient cycling. And we talk about nutrients, we really sort of talk about nitrogen and phosphorus. But all of these services and health issues within these systems can be tied to when, where, and how much sediment is involved. And when I talk about health issues, I mean water quality and clarity. So how do we bring sediment and bed shear stress? How do we sort of bring those two concepts together? Well, when I talk about bed shear stress, I'm talking about this tau b parameter, and it's proportional to the velocity gradient, the horizontal velocity change vertically through the water column. So as a flow interacts with the bed, or a tidal flow interacts with a sediment bed, you have a boundary layer that develops, similar to this cartoon on the left. And as that velocity gradient changes in space, you get a shear stress value. And when that shear stress exceeds some critical threshold, you have incipient motion, the earliest stages of sediment transport. And when you greatly exceed this critical threshold, you then get sediment resuspension. This critical parameter is generally found using a Shields parameter, Shields curve. That's dependent on the sediment grain size and the boundary layer conditions at the bed. The limitations of using this value is that it was based on non-cohesive sediments and a flat bed in a laboratory, but generally it's a good first estimate. So we're interested in looking at the distribution of shear stress as it relates to some critical value. How might tides and waves be different in terms of their boundary layer dynamics? So tidal boundary layer is similar to the one shown in the previous slide, and generally shear stress due to tides is found either using a quadratic drag law or a logarithmic law of the wall, both related to some velocity squared. Looking at a wave boundary layer, you find the shear stress due to waves as a function of some frictional wave factor and the orbital velocity at the bed. If you take a look at just the difference in the slope of these two values, you can see that wave boundary layers can produce a higher instantaneous bed shear stress, but they don't last as long as tides. So there's sort of this time dynamic difference between waves and tides. If you combine the two, looking at combined wave current flow, that's sort of suggesting when tides and waves work together, they're much stronger, but the angle between the two can change how that shear stress is determined. So this is one of the things we'll be using later on as well. Where we're studying the shear stress distribution and boundary layer dynamics is the Great Bay Estuary. It's one of 2 estuaries located in New Hampshire. It's one of 28 estuaries of national significance as designated by the EPA. It's part of the National Estuary Program. It's tidally dominant in some of these natural constrictions. You have tidal currents on the order of 1 to 2 meters per second. It's a mesotidal system, 2 to 4 meter tide range, has relatively low river input, only 2% of the tidal prism, and it's characterized by deep tidal channels and fringing large mud flats like the one you see above. Similar to estuaries across the United States and the Earth, it's been showing signs of eutrophication, so degraded water quality and clarity. The Piscataway Region's Estuaries Partnership is charged with studying this estuary and sort of coming up with estuary health indicators. They had a State of the Estuaries report in 2018 looking at trends. I'm just showing nutrient concentration trends for the Great Bay. That nutrient loading, nutrient concentrations are a cautionary tale. And if I'm going to sort of just pick dissolved inorganic nitrogen in terms of nutrient loading, if you're looking at point sources like from wastewater treatment plants versus non-point sources, we have a decent idea of where non-point sources are coming from in terms of fertilizer runoff, septic system, animal waste, atmospheric deposition, but none of these estimates incorporate sediments. So I'm sort of thinking that sediments might be an important non-point source that should be considered, and that's sort of in line with what we're trying to get at here. So how does shear stress and nutrient loading, how are they connected? Well, as I said before, if you apply a particular shear stress, you exceed some critical threshold. That shear stress is a function of the hydrodynamics. You exceed some threshold, you get sediment resuspension. And if you exceed it enough, you then get nutrient release associated with that sediment resuspension, either from pore water getting released or sediment as a part of a sediment itself. But of course, if you're talking about nutrients, you really need to know where the mud is. So we need mud distribution in the bay. As a part of previous work, using sediment at Adams Point, incipient motion has been found to be 0.1 newtons per meter squared. And if you're talking about nutrient release, 0.35 newtons per meter squared is sort of our threshold there. So those are two numbers to remember. But this is based on observational work at one point in the bay. So we really need shear stress estimates everywhere. So this sort of goes in line with validating, developing a numerical model and taking a look at what shear stress might be across the bay. So in terms of our big question, I came up with 4 steps that sort of fall in line with this research. 1, model the hydrodynamics. So I'm going to spend a significant portion talking about the model. Then I'm going to show distribution of bed shear stress over a typical tidal cycle. And then I'm going to introduce the role of vegetation. And for the first time, we've actually measured waves in the bay. And this is sort of a first stab at modeling and investigating the role of waves. So modeling the Great Bay, first step took a long time, just constructing a stable model grid because the flows are so fast and the topography changes pretty rapidly. We used a couple different data sets to create this model grid. LIDAR from the USGS, FEMA, and NOAA. We incorporated land that was above mean sea level. We were looking at future inundation studies possibly being used with this model. The Army Corps river surveys, so each of the 6 or 7 rivers that feed into the bay, depending on what you're looking at. The CCOM Joint Hydrographic Center Western Gulf of Maine 8-meter bathymetry survey covered sort of the offshore portion of our bathymetry. And then we actually went out and collected bathymetry of the Great Bay and Little Bay in the winter of 2015, 2016. You can see John Hunt and the Galen J up there. It was really important to us to have current bathymetry in order to sort of look at our currents and believe them. It's gridded to 30 meters horizontal resolution. The model has 8 vertical levels, and again, it includes up to 20 meters above sea level. We use the COAST modeling system. COAST stands for Coupled Ocean Atmosphere Waves Sediment Transport Modeling System. For this first part, we're only looking at ROMS, which is the ocean model portion of it. It's the Regional Ocean Modeling System. It's a 3-dimensional free surface topography following numerical model. It solves the finite difference approximations of the Reynolds average Navier-Stokes equations, and it includes hydrostatic and Boussinesq approximations. And in order to step the 2-dimensional and 3-dimensional time, it has a split explicit time stepping algorithm. So this is how we took the grid, took our model, and set up our runs. We force it with the tide, subtidal, and river forcing. I'm only talking about tidal today. The tide was driven using the Oregon State tidal prediction output, and that incorporates tidal velocities offshore as well as tidal elevation. Looking at the M2, S2, N2, O1, and K1 tidal constituents. And if you take a look at the right, this is what NOAA's output for the time period that we ran the model from in 2015. And we get our subtidal forcing from this data. The lateral boundary conditions, it's closed on the north, east, and west side of the boundary, or of the model, and it's only forced on the southern boundary. Our bottom boundary condition is really important in order to understand the tidal dissipation and tidal dynamics. So we pick a logarithmic drag law, which is pretty common in coastal areas. We pick 4 different bottom roughness characteristics, 0.015 to 0.03. How the model represents shear stress is through we choose a logarithmic drag law, and this is where our parameter comes into play. And it's spatially uniform in this run. Wetting and drying is incorporated into this model. It's important to both flood and dry the mudflats. That's sort of an important numerical addition to ocean modeling worlds relatively recently. The data was output 30 days. In order to look at shear stress, we output it everywhere every 30 minutes, took an average value. And we took 5-minute station data in order to validate how the tide changes and transforms as it enters the estuary. And you'll see in the next slide, we take station data from offshore every 100 meters across through the Piscataqua River, Little Bay, and all the way to the Squamscott River. We're taking a look at how the tide changes in these locations. How do we validate this model? We use 4 different methods: tidal analysis and dissipation. We compare the currents, and we're only looking at comparing modeled currents with observed currents in 2015, and that's these black diamonds are where we deployed instruments in 2015 to take a look at tidal currents. And then we do a cross-spectral analysis and look at the growth of the tidal harmonics. So if you take a look, the red line indicates our station files from offshore to the Great Bay. This figure shows from the ocean all the way to the Great Bay. The bottom panel is the depth along that transect. The top panel is normalized energy of the M2 tide. So we take the amplitude of the M2 tide, which is our most energetic tidal constituent, and we look how that changes from the ocean all the way to the bay. The dots are the observed estimates of that change, and the model is the solid lines. And you can see that the observed shows some amplification of energy, but then you see about a 45% decay in that M2 tidal energy as you go from the ocean to about between Dover Point and Adams Point, and then it flattens out in the Great Bay. So this sort of suggests there's a highly dissipative environment through the Piscataqua River, and then the tide flattens out. You can also take a look at how the M2 tide, the phase shifts from the ocean all the way to the Great Bay. So how that phase shifts is by about 50 degrees. And what that suggests is that when it's high tide in the open ocean, 2 hours later, it will be high tide in Great Bay. So that's sort of a first stab. The model gets those large scale dynamics. Next, we're going to look at velocity comparisons at this particular ADCP in the Great Bay. And this is the horizontal velocity components at 3 different points vertically in the water column. You have the east-west velocity and the north-south velocity, comparing the model, which is dots, and the observed, which is the line. If you take a look, the model represents the magnitude and the pattern of those currents relatively well. And the RMS errors are only about 4 to 6 centimeters per second, which is pretty good if we're only driving this with the tide, and these are observations. This ADCP was in about 6 meters of water depth. So we can maybe think that we're getting the velocities pretty well throughout the water column here. The next way we validate the model is looking at cross-spectral analysis and the higher harmonics. So again, going from the open ocean to Great Bay, we're looking at the PU phase, the ratio of the M4 and the M2 tide, and that phase difference. When I talk about the PU phase difference, it's a pressure signal and a velocity signal. At the open ocean, we would think that the pressure and the velocity signal are in phase. It's a progressive style wave in the open ocean. But as that tide progresses onto the continental shelf and into shallow water, it changes. So what we see is that progressive wave, even at Fort Point, is almost about 45 degrees. So not necessarily 0, but it's more progressive than standing. And as you see that PU phase change to the Great Bay, it changes to about 90 degrees. So in the Great Bay, you have a standing wave. You have your high tide and your fastest velocity shifted by 90 degrees. And that's what we see in the Great Bay. So that's an important aspect that the model needs to represent. Now, when we're talking about the growth of the nonlinearities, this is a really important sort of aspect that the model should represent. The M4 is the first harmonic of the M2 tide. And it's been suggested that the growth of the M4 tide is actually sort of a sign of how nonlinear this system is. So you can see that the model doesn't necessarily get the growth of the M4 everywhere, but you can see that it grows a bit in the Piscataqua River and then quite a bit in the Great Bay. That's because the Great Bay gets pretty shallow pretty quick if you're talking about a tide. Another really important aspect that this model represents is the ebb dominance or flood dominance of this system. And if you take a look at the phase difference between the M2 and the first harmonic, the M4, you can see if it's between 180 and 360, it's an ebb dominant system. This has been found looking at other estuaries too. And if it's less than 180, it's flood dominant. So in the Piscataqua River, you have an ebb dominant system. You have short, quick ebbs, longer, lower flow floods. But that switches as you get to the Great Bay, which we'll see later. You have short, quick floods and longer, lower flow ebbs. And so I included this because I think this is a pretty important result that you'll see throughout the rest of the next couple topics. So summary, the model reproduces the tidal dissipation, velocities, evolution of the higher harmonics, and that cross spectra, so the standing versus progressive wave, just looking at tides. And we found a bottom boundary condition that works well is the 0.02 meters. So this is what we'll be using in all of our future modeling studies. I didn't talk about river flows and subtidals, but they have weak interactions if you're looking at the bulk tidal dynamics in the Great Bay. And for further information, you can look at that paper. So back to our steps. I spent a good portion talking about the model because I think that's important if you have a validated model to then start looking at what we can do with that model. So next I'm going to take just the output and show you what the distribution of shear stress is across the bay. How the model does this, as I showed before, we have 8 vertical levels in our particular model. We don't have sediment turned on, but if you take a look at the bottom box of the model and zoom in, you have a U velocity on this face and a V velocity on that face. This is estimated by the model. Taking our Z0 value of 0.02 is what we prescribe in the model. This is using a logarithmic boundary layer that's what we choose and sort of set the model to be. This is where that 0.02 comes into play. Now, observationally, there have been 2 studies that I've looked at to compare the model. In June 2011, Wengrove and Foster Wengrove et al. Described some shear stress estimates during Tropical Storm Irene. That I won't talk about here, but that will be important later. We take the model and we estimate shear stress to a time in July 2016 to match the tidal conditions of Karakuchi's deployment. She deployed an aqueduct and looked at calm and flood ebb tidal estimates of shear stress using high fidelity velocity measurements near the bed and analyzed it over 4 days. She also used the logarithmic law of the wall formulation, but found a shear velocity using an indicator function. So this is our observational estimate of shear stress. You can't measure shear stress directly. Just want to make some points. You need those high velocity measurements, high fidelity velocity measurements near the bed. And observations in one place, her blue stars where she deployed the instrument that we're looking at here, is not representative of the entire bay. So this is what the model outputs at low tide, right? We have a standing tide, so you have low flows at low tide and low flows at high tide. This is the distribution of shear stress, just one point in time. You have shear stress from 0 to 1. Remember, 0.1 is what we're using as incipient motion, and 0.35 is the release of nutrients, and 0.35 is just the shaded figure. Now, if you're looking at a flooding tide, it looks a bit different. You have really strong shear stress values across the mud flats, which is where we're interested in this sediment resuspension. And then you have high tide again, low shear stress everywhere, low flows, right? You have not high flows at high and low tides. And you put it together and you get something that looks like this. So this is run using the same tidal conditions as that deployment. And later I'll take a time series of where Kara's instrument was and compare it with model outputs. High tide, low shear stress, ebbing tide, strong shear stress in areas, low tide, not as much. You see drying of the mud flats, and then high tide again, ebbing tide, and you'll just see again, just to point out that the model does get the wetting and drying of the mud flats. So we've modeled the hydrodynamics, investigated and modeled the bed shear stress. We have estimates of shear stress across the entire estuary. during a couple tidal cycles. And we've actually run it for an entire month. So now I'm going to talk about incorporating vegetation into this model, and then I'll talk about nutrient loading after incorporating vegetation. So the role of vegetation. So this is the second paper. The influence of submerged aquatic vegetation on modeled estimates of bed shear stress and nutrient fluxes in a tidally dominant estuary. The model has a vegetation module. It incorporates waves too, but we're not including waves yet. We're just looking at how this vegetation module and ROMS feed back to each other. So ROMS gives this vegetation module, depth varying currents, and then it gives a drag force, which I'll talk about in the next slide. How we figure out where the eelgrass beds are using data sets from granite and seagrass net. And this is the distribution during 2016 of what the eelgrass is. And if you zoom in where Kara's site was, it's right on the edge of an eelgrass bed. And why eelgrass is important, right? It provides habitat, damps currents, promotes sedimentation, and provides nutrient uptake. So it's an important component to investigate. So modeling vegetation, you see that boundary layer without vegetation, you have shear stress, high shear stress at the bed. You would imagine that there'd be higher sediment transport here. You can see that submerged canopy and emergent canopy changes the boundary layer a bit. It does damp the flows and promote sedimentation. How the vegetation incorporates a drag force is incorporating a plant drag coefficient, individual plant width, and number of plants per unit area. And so we run two case studies where we look at a dense canopy, 2,500 stems per meter squared, which is found using some studies that were done at MIT, and a sparse canopy, 800 stems per meter squared, about 30%. And this is based on data of eelgrass bed. In 2016, it was found that in July, the eelgrass beds weren't very healthy and they were about 30% abundance. And this is a picture of eelgrass in the Great Bay. So taking a look at our no vegetation case, I want you to look at the left side of the screen. This was based on the first model run. You see it's a flooding tide. Those vectors show the speed of the currents. So you can see it's stronger in the channels, not so strong on the mud flats. And that shear stress value just during that flood tide max current. Now looking at the dense vegetation case, you can see where the eelgrass beds are. I sort of taper it from really, really lots of eelgrass to not as much because you get some instabilities if you just have one eelgrass bed and nothing. And then now we're looking at the distribution of bed shear stress incorporating vegetation. And if you squint, you can see areas where there is eelgrass, the shear stress is lower. So it does do what we think it does. And if I take a look at that 0.35 Newton per meter contour, where nutrient release might be important, on those mud flats where there is vegetation, you can see it's lowering that shear stress value to below 0.35 newtons per meter squared, providing a mask to these sediments. If I put that together, including that 0.35 Newton per meter contour, you get something that looks like this. High tide, right, low shear stress values. But then as the tide comes in and you have those max currents during mid-tide, those areas are damped. And during flooding tide, those areas are damped or are sort of masked. Cool. Flooding tide, yep, where those eelgrass beds are, they're important. All right, so taking a look at a time series comparison. This is taking Kara Cucci's output from her observations, averaged over flood and ebb phases. She did an analysis for 4 days using a log law of the wall. We take model output of sea surface height, depth averaged velocity, and bed shear stress, comparing it to Kara's estimates. I just want to look at the flood tide to begin. So taking a look at, we have a 30%, so zero vegetation case, 30% vegetation case, and 100% vegetation case. So the flood tides are about 20 centimeters per second. In each case, the model underrepresents those flood tides, but gets the pattern well. You see that as you increase the amount of vegetation, you damp those currents. Taking a look at the bed shear stress values, Kara averaged it over an entire flood, so about 0.25 newtons per meter squared is what she found. And the model sort of hits 0.25 going from July 8th to July 12th. If we take a look at the ebb tide, her observation should suggest it's about 0.15 newtons per meter squared. If we take a look first at the depth average velocities, you see the pattern is that the velocity grows, decreases, and then grows again. And the model represents this sort of this pattern, and even the model including vegetation represents it much better than not including vegetation. So that would suggest that vegetation has some sort of influence on the flows in this area. But the shear stress has a large spread, right? Observations, it's hard to observe bed shear stress or observe currents and get a bed shear stress estimate. But in general, if we take a look at Kara's average value, if we look at the vegetation level, the vegetation estimate, it does sort of match her value in magnitude. So to summarize, there is a velocity asymmetry that we're getting, right? Flood dominant systems, strong floods, longer, lower flow ebbs. There is a asymmetry in the ebb shear stress, but we might overpredict it a little bit. In general, vegetation helps these estimates. Not shown, we ran a 10-meter case as well as a 30-meter case, and the 10-meter grid didn't perform any better than the 30-meter grid, which would suggest that the 30-meter grid is fine for these kinds of studies. So, modeling the hydrodynamics, modeled shear stress, incorporated vegetation. Now I'm going to talk about how all of this affects nutrient loading from sediments. So how do we do that? How do we apply this model to answer that question? First, we need to find an area with greater than 50% mud fraction. Then we need to, so based on previous work, then we need to find an area that's greater than 0.35 newtons per meter squared and greater than 50% mud fraction. And that uses model output and lab studies, because that 0.35 newton per meter number came from lab studies. And then following the same procedure that Wengrove et al. In 2015 made, we provide this area here and follow the same procedure. They found an estimate of an event based on Tropical Storm Irene. We're looking at a typical tidal cycle. These values of 1.3 millimoles dissolved inorganic nitrogen per meter squared and 0.21 millimoles of phosphorus per meter squared came from these lab studies. So, nutrient loading. How do tides compare to other sources? Well, first let's look at other sources. Based on rivers, seasonal events, seasonal component of rivers, and just looking at dissolved inorganic nitrogen in kilograms per month, you can see a seasonal pattern. Fall, winter, and summer about between 2,000 and 4,000 kilograms per month, with the spring freshet, you have a sort of a large peak in the spring. If we just take a look at sediments without incorporating vegetation, we estimate about 750 kilograms of dissolved inorganic nitrogen per month. Phosphorus is a bit of an interesting story. Uptake isn't considered. There's some biogeochemical further work that needs to be done looking at phosphorus, but we estimate about 300. Now, if we incorporate that run with vegetation, we get 614 kilograms per month, about an 18% reduction in dissolved inorganic nitrogen by looking at the inclusion of vegetation. So that's pretty cool. Event-based estimates. So if we're taking a look at event Tropical Storm Irene, based on Wengrove et al.'s work, not including vegetation, for their bed shear stress estimate across the bay, they get about 220 kilograms of dissolved inorganic nitrogen per that event. Now, if we take a look at during a typical tidal cycle, I'll show you an average tide, a neap tide, and a spring tide. So during an average tidal cycle, we get about 25 minimum, neap tide 13, and then 100 kilograms per event. So about half of what Wengrove et al. Suggested. They had enhanced flows and winds as well. If we include vegetation in every case, vegetation lowers this estimate by between 20 and 40%. So it's important to look at vegetation when you're sort of considering this kind of work. And to answer our first question, yes, sediment resuspension and nutrient release from sediment resuspension is potentially important If you get the right critical threshold right, and if you get the right resuspension nutrient release numbers right, it's important and significant on every tidal cycle. So we've done the first 3 steps: model the hydrodynamics, investigate modeled bed shear stress, and we've looked at the role of vegetation. Now I'm going to talk about measuring, modeling, and investigating the role of waves. So this is paper number 3, looking at the spatial and temporal distribution of shear stress due to waves and tides in the Great Bay. So in the summer of 2018, we went out and deployed 4 spotter buoys and 1 AWAC. And this is just a movie of what the wave conditions when we went to check on one of the spotter buoys. So I just want to give a little bit of background about waves in the Great Bay. We're looking at small amplitude waves, less than 20 centimeters. We're looking at summer conditions. These are kind of ambient conditions. They can be important for sediment resuspension in estuaries, and they aren't generally looked at, but plenty of studies have looked at them in other, well, a couple of studies have looked at them in other shallow estuarine environments with mudflats and found them to be important. And one of the most cited works is actually from the Great Bay, Anderson, 1972. In August and September, went out and put an electromagnetic wave staff. If you've been at Jackson Lab, and that little cove just to the south of Jackson Lab is where this study was conducted, under mild winds and waves about 3 to 5 centimeters. So what you would expect is during an ebb tide, as the flows get faster, so this is sediment concentration and wave height. So he showed expected values for sediment concentration to be strong when the flows were strong. But in fact, they observed a peak in sediment concentration in the water column when there were waves, suggesting that waves are actually driving some of the sediment transport, not necessarily what you'd expect just from tidal currents. It's similar on the flood tide. As you would expect, the expected value of sediment concentration goes down because the currents went down in this situation. But then there was a 4 to 5 centimeter wave event in that cove, and observed sediment concentration went up. So waves could be due to wave action, but waves are actually really hard to measure. And you can see here, we deployed a wave staff and got a lot of biofouling from eelgrass. So this was just outside of a channel. We really want to measure waves in really shallow environments, but they're really difficult to measure. If you put a wave staff out, you can have some biofouling. So it's a pretty hard observational problem. But we attempted it anyway. So we put 4 spotter buoys out, generally in the channel here and here. We have an AWAC, which is an acoustic wave and current profiler. And then we're using winds from meteorological station in Greenland. And we had our wave staff over here, but haven't looked at that data because we have some biofouling issues. So next I'm going to show what the meteorological and wave climate is in the Great Bay generally over the summer of 2018. Oh, well, first I'll talk about the model. So now we're looking at both ROMS and SWAN, and we're using this model coupling toolkit. So that is how ROMS and SWAN, or ocean and waves, talk to each other. So I'm going to talk a little bit before I look at results about simulating waves in the nearshore, which is our wave model. It's a 3rd generation spectral wave model, and it simulates the evolution of an entire wave spectrum. So it doesn't resolve waves themselves, it resolves how a wave spectrum moves in space and time using wave action balance equation. So this is how SWAN works. In general, you have wind blowing over a body of water. You get initial ripples and wind waves, and then a fully developed sea, and then you get swell waves. We don't have swell waves in the Great Bay because waves don't propagate from offshore into the Great Bay. We're only looking at wind-driven waves. And how those waves interact with the bottom, if you have waves developing based on their wavelength, developing in deep water, they propagate onshore, and they start interacting with the bed, which changes both the bed state and the waves themselves. So this sort of propagation from deep water into shallow water is an important thing that we're trying to model because it's hard to observe, right? So we can't observe in this shallow area, but maybe we can model waves transforming into that area. And how we do that is using this wave action density parameter n, and that takes the wave energy in terms of radiant frequency and direction and divides it by frequency. And it does that because this quantity is conserved as waves are propagated, but wave energy actually isn't. So taking this wave action, moving it in space, in X and Y space, in frequency space and direction space, is really a function of your inputs and your outputs. And we have wind input, we have dissipation, and we have nonlinear interactions. And these are really important in shallow water, particularly when waves transform from deep to shallow water. Dissipation in the form of white capping bottom friction is what we'll really be interested in, and depth-induced breaking. So this is the meteorological and wave climate in the summer of 2018. The top two panels are from the AWAC, looking at sea surface height and depth average velocities over from the beginning of July to the end of August. You can, if you squint, maybe you can see the spring neap modulation. You can certainly see it in the currents. So the next two panels are from the meteorological wave station. So looking at wind speed and photosynthetic active radiation, and also wind direction. So the reason we look at photosynthetic active radiation is that's just sort of telling us daytime, nighttime. So our winds are really following this daytime, nighttime pattern. And you can see there's a lot of variability in the wind direction. In general, it follows a sea breeze, land breeze sort of direction. So you have waves coming from the east-southeast or sort of the west-northwest quite a bit. And now this is sort of our spotter buoy output, looking at significant wave height and peak periods of those waves and those locations in the Great Bay. So we have 4 buoys that go up until about July 17th. One of our buoys malfunctioned after this, and then a boat actually cut buoy 80 off. So we only had data up until here. But we're gonna take a look at model results from this first sort of section. But in general, the waves we're seeing are between 5 and 10 centimeters. There are a couple events that are above 10 centimeters. So these are those small amplitude waves that we're interested in. Peak periods are between 1.25 and 2.5 seconds. So I'm going to zoom in on that first part, right, where we have all 4 buoys out, taking a look at sea surface height, depth average velocity from the AWAC. So those are observations. Looking at wind speed. Wind speeds are about 2 to 3 meters per second, so mild conditions. And wind direction, you can sort of see a pattern much easier when you zoom in a bit. We look at 2 different case studies. I'm only going to talk about one of them today. We have a sea breeze case and a land breeze case. Sea breeze is from the east-southeast, about 115 degrees, and the land breeze case is from 270. In each of these cases, you get waves over 10 centimeters. So we're going to model these conditions and see how well we do. So this is our sea breeze case. Blue indicates spotter buoy 80. The model is in solid line. The observed is dotted line. The top panel is significant wave height. The second panel is wave peak period. Model is the solid line. We only find peak periods for times where there are waves. And then the third panel is modeled wave direction and wind direction. So we don't really believe the spotter buoy wave direction. We're having sort of some problems getting that out of the wave buoy. So we compare, if the winds are blowing in this direction, we'd expect the model wind directions to go in the same direction. So we compare those. And then the bottom panel is sea surface height in the dotted line and modeled velocities. We don't have observed velocities in those areas, so we take a look at modeled velocities. That might give us a bit of an indication about that wave current interaction or that combined wave current flow. You can see the pattern here is that the model starts with no waves, gets some waves, and then goes back down. So it has the pattern, but it's under predicting the significant wave height. Similarly, as wind blows across the bay, you have a growth in the wave period and then a decay in the wave period, but it's under predicted by about 0.5 seconds. You can see that the modeled wave direction changes and then flattens out. And I believe this change has to do with the changing currents. It happens again over here. So that's the case for buoy 80. We see this pattern in all of the buoys. So buoy 74 is green. It's located in the southwestern portion of the bay. And you can see waves grow and then decay but not quite representing the significant wave height we see from the buoys. And you see a similar pattern in the peak period. And similarly with 71 and 73 on the western portion of the Great Bay, you see that pattern. So the model is presenting waves, but it's under predicting those small amplitude waves. So I'm going to sort of zoom out and take a look at the Great Bay as a whole. What do wave heights look like across the entire bay? So this left at this particular time. So the top panel is modeled water level, and these vectors are showing wind direction and wind speed. So for this sort of low to high to low tide, you have winds out of the east southeast for about for a while. And we're going to pick this one time point, and then just buoy 80 for reference. You can see that there aren't waves in the southeastern portion of the bay, but there are waves sort of in the northwestern portion. So it is creating waves and propagating them. But you can see that they're kind of arrested in the channel, and that's because there's ebb currents. So it's an ebbing flow. So you can imagine that the waves propagate, interact with the currents, and then there's this sort of shadow on the other side of the channel. Same sort of thing happens in this channel. And you can see a large shadow on the north side of the Adams Point. So that's the wave conditions, currents. These are modeled. Taking a look at just the 0.1 newtons per meter contour, you can see that the combined shear stress. So this is showing combined shear stress with large values in the channels, with low values out on the mudflats. There might be some resuspension or incipient motion on the inside portion of that contour. And now we're going to look at the ratio of waves to currents. So how important are waves compared to currents? So taking that bed shear stress value of waves and dividing it by currents, you can see that areas where waves are important, and only by half compared to those currents, I mean, we have small waves, they're in areas where there are waves. So we would imagine that waves are important where they exist, but also where they exist and are stronger than currents. So they're about 50% of the currents in this area. So even if the currents are not very strong and they don't exceed that incipient motion threshold, if you have waves on top of it, it might boost that a bit. In looking at our steps and our research question, we've done the first 3 steps, and step 4 is we measured, modeled, and investigated the role of waves in the Great Bay. I gave sort of an orange check mark here because we've measured them, but we've only done sort of a first stab at the model, and we sort of need to go back and investigate what the model, why it's under predicting that significant wave height. So these are my major conclusions: that coast and ROMs, the model does a good job of representing those bulk tidal behaviors. The distribution of shear stress matches observations. There is an asymmetry in the tidal currents that requires some future investigations. We're still under predicting that flood tide. We made the first estimate of estuary nutrient fluxes from sediment using numerical models. It suggests that sediment resuspension is an important mechanism for nutrient loading, and that vegetation actually improves that performance, and it decreases the nutrient load estimates from sediments. Waves were measured for the first time across the bay, and the model suggests that waves are important in those shallow fringes, but it doesn't quite capture the magnitude of those wave characteristics yet. Future work for any new students that are interested, I have a lot of it. Investigating waves and combined flows and wind-driven currents. We haven't looked at wind-driven currents here. Dispersion and small-scale mixing, there are some studies using drifters currently to take a look at that. We actually have a lot of data on sediment. We have a lot of historical data on sediment type across the bay. So incorporating a distribution of sediment, looking at sediment transport studies, finding a spatially varying drag coefficient Z0, not just a single value of that 0.02, and investigate the role of waves, tides, and vegetation. So using that vegetation module with waves as well. And with that, I'd like to thank Tom, my entire committee, everyone who's helped in this research. my friends, Michael Hitchcock, my family, and many others that I haven't named here, and the supercomputers that did a majority of this work. So, thank you. Yeah.
So we have time for questions from the audience.
Yeah, Cal.
Thank you, Salme. Is this on? Or is that just my voice is always this loud? Okay. So working for Piscataqua Region Estuaries Partnership, and I just want to say that this is fantastic and that the director, Rachel Riard, is here, and I can see that she's nodding already. It's very difficult to overstate how important this work will be for us, honestly. It's very, very impactful work. So thank you and all your colleagues on this. I had a question about the fact that you were saying that it takes, the estuary spends more time ebbing than it does flooding. Or can you clarify that? And just to let you know where I'm going with this is, a lot of times when people are talking about sort of the volume of water in the estuary, they just think, well, it spends half its time at, they just divide it in half, right? And I guess I'm wondering, is that an incorrect assumption, and that actually the bay spends more of its time at sort of less than half filled? That would be very important for things like nutrients, because if you look at it on a volume basis, then that's important.
Yeah, it's not necessarily that. So thank you for your question.
Yeah.
It's not necessarily that half the time is spent flooding and half the time is spent ebbing. The flood tide and the ebb tide are equal in time. It's just that when the currents are max and when it is in its flood stage, it's short and quick and much faster than the ebb flows. So the time it takes for it to ramp up and get maximum is much shorter for the flood than it is for the ebb. In terms of how much time a water parcel spends in a particular time in the bay, I don't actually know the answer to that question, and that sort of involves some future work looking at the model. Yeah, right here. Sorry. Right here.
So I echo, very nice job. One thing that I'm having a hard time getting my head around, and I think it's really important for one of your conclusions, is I guess I can sort of see the magic of 0.1 Newton for starting to move mud, if it's all the same.
Yeah.
But how can you take that and say 0.35 is when you're going to get nutrients? Because it has to depend on the nutrients in the sediment column. And
so that's,
that to me, that seems like a black box sort of a number. And how confident are you in that? Or how could you make a better guess at that?
Yep. So that number, it is one number that represents a large portion of the Great Bay. So that number came from a couple of lab studies where they took an entire core of sediment and overlying water, and they applied a known shear stress through a spinning motor. And then they took measurements of nutrients from the water column every 15 minutes as that shear stress was initially moving sediment and then resuspending sediment. So it actually looked at a time series of how nutrients were getting introduced into the water column, taking a couple different samples from the Squamscott and from, I think, next to Adams Point. There was another study that was done using similar samples that found, so 0.35 was during a really strong event, right? So there were other numbers suggesting maybe 0.2 newtons per meter squared is an important number. In general, 0.2, 0.35, if you're there, you're resuspending sediment. It's just the amount of nutrients, I think, is what changes. And that is definitely future studies. But 0.35 was found in a couple of different sediment cores from a lab. Yeah. Yep. Ben. Right here. Yep. Lobster guy.
Nice work. Even if I understood about maybe a third of it, so I am but a big dumb ecologist and all the math goes over my head. But because I am a big dumb ecologist, I tend to wonder about the biotic effects. And you mentioned that the shear stresses are greatest on the low tide period, right?
They're greater on the flood.
On the flood.
Because there's stronger flows, but there's still strong shear stresses on the ebb.
Right. So mostly I just happen to know that a lot of the biotic activity occurs at high tide because there's more mudflat exposed. So if you look at how the dissolved nutrients are distributed in the water column, does that comport with what you'd expect based on your modeling here, or is there perhaps a substantial component of things that move around and bioturbate that add those loadings at other times as well?
So you're seeing higher biotic activity at high tide?
Correct,
So you're-
because they can come out and play on the
Come out
mud
and
flats
play.
that are otherwise exposed.
So my question is, are they coming out and playing because there's water or because there's more goodies in the water column for them to?
Horseshoe crabs definitely are coming out because there's water. They can't really access
Yeah.
it on low tides.
So could you, I guess, restate your question in terms of some of that? I was just sort of
Yeah,
trying
sorry,
to.
so I may have missed it, but
Nope.
when you're doing the nutrient stuff,
Yep.
Did you actually have measurements of in situ dissolved components?
No.
Okay.
Yeah.
So that might be a useful next
Yeah.
step for somebody else to do.
Yeah, for sure. And I think so the dissolved or the nutrient portion came from that lab study. So that was a really, really important study that connected modeling observed physical characteristics of flow to nutrients. So more of those studies I think would be really important, particularly during different types of hydrodynamic forcing, right? So they did take a core about this big and apply a shear stress to it. And I will actually find a zoomed in. Just take a look at the, yep. So here, this is sort of the setup, right? So we had, this is the core itself and that's the motor, and then taking samples of the water. So it's whatever was in the water at that time. Yeah. Definitely a good area for future work, I think. Yep, right here.
Well, good afternoon. That was great.
Thanks.
In light of what he was saying, the bioperturbation caused by polychaetes and mussels and clams had a big effect in Chesapeake Bay on releasing nutrients.
Yep.
But that water is exposed to the water column all the time.
Yep.
And it'd be very interesting to compare the short duration versus the other sources of nutrients that would be going on. So that's a very interesting question.
Yeah.
But on a second hand, my question was about your boundary conditions. Why did you set the boundary conditions where they are offshore, and how far offshore did you go?
We went offshore about 6 kilometers, just inside of the Isle of Shoals, because we weren't interested in looking at the currents around the Isle of Shoals just yet. Certainly that could be future research. But we chose, do you mean why did we choose those constituents of the tide as a tidal boundary out sort of offshore?
Well, why did you go offshore versus just at the channel, at the mouth of the estuary?
So the first, yep, great question. So the first study I did in the first couple years of the PhD was actually right at the mouth of the Great Bay, and then moved up to the Little Bay. But really, in order to get the tides right in the Little Bay and Great Bay, we wanted to see how the tide changes as it propagates through the Piscataqua River up through the bay itself. And just using tides offshore as a boundary condition in the Little Bay, it's changed so much as it went through the Piscataqua River. So really, we would need observations right at the Little Bay to get the conditions right for the Little Bay and Great Bay. So I guess I can go back to just showing, yep. Great, so as the tide propagates, if we just started it right here, which we can, but we would need to know how the tide changes from here to here, because the tide is the majority of our forcing. So we really, this just seems like a more complete way of looking at the whole system. Does that answer your question? Okay. Oh, sure. Will? Oh, sorry, Bill. Sorry.
Thank you, Salme. I was wondering what effect or what information, I guess, can we get from existing landforms, like existing mudflats on the currents and kind of, I guess, the bulk behavior of the estuary? Is there, has there been any work on that?
You mean like how the mud flats change like current behavior, or change like?
More like what the location and shapes of the different landforms can tell us about what's going on in the
Like the geological sort of aspects of that, like where they are and.
Yeah, where they are and how they're shaped, what that can tell us about the currents.
Right, so we already know a bit, even if you just went out and collected a survey or saw where the tidal channels were versus where they're not, they lead to rivers. So what it tells us is that river currents acting with tidal currents maintain these channels. We have 2 bathymetric surveys, one from 2009, one from 2015 and 16. They don't change that much, which suggests that the system is pretty stable. And knowing that we have short, quick floods means a lot of sediment is picked up and transported and pushed onto the mud flats. So we have sort of this inundation of sediment that's helping the mud flats stay in its current form. That's that flood dominant system. If we had stronger ebbs, then we would probably be exporting sediment more than we're importing. So the mud flats themselves are pretty stable, and we can probably take a look at a transect across from a channel to a mud flat and estimate how the currents might be changing across there. But the mud flats themselves are in their orientation and are pretty stable. And the channels are because they're just river flows that act with tides to sort of maintain them there. That helps, you know. Anne.
Those of us who have spent some time thinking about flows through vegetation know that it's very complicated, and this is a really nice application of, from what I can tell, an off-the-shelf use of the ROMS module to see how it might affect things in Great Bay. I was wondering whether you could use your observations from the tidal channels to constrain that and see whether the model itself was representing the vegetation correctly, or whether the model itself could be improved in its representation of eelgrass.
Yep. So do you mean the flows in the channels with and without eelgrass to see what those changes might be?
Right. I guess I was surprised that before, from what I could tell, before you incorporated eelgrass, it seemed like you were getting the channel flows correct. Maybe I wasn't.
No, I'm going to go take a look.
Maybe I misread that, or maybe, you know, looking at the residual tells you something about what the eelgrass is doing.
Yeah. I mean, I've been staring at this longer than you guys have. So it's hard to sort of, so we under predict this flood tide. And I think that this is an area certainly of sort of a top-down view of what are the currents doing in the area where Kara's instrument was. This is certainly an area I want to take a look at. It suggests that the model isn't allowing the flow to either channelize in that area, or it's just because we have a 30 meter by 30 meter grid and it's not maybe representing something. But in terms of the ebb flow, we're getting that right, and we're getting it right much better than just the 30 meter grid. So I think that on the ebb tide, the vegetation does represent the flows correctly. But as you're suggesting, on the flood, there is some work to be done, certainly on looking at how that flow enters this region. And I think that the model definitely can be improved, particularly in this part. Yep. Right here? Yeah. Oh, yeah, sorry about
So my question is, I'm wondering how limited your logarithmic shear stress representation is, given the fact that you have your wind-driven wave modes, your eelgrass maybe giving nonlinear effects, your strong flows, things like that.
Yep. So logarithmic is sort of the best guess we have, but there's certainly a lot of times where that breaks down. And particularly when you have flows that are, so you have tide coming in, and then we have some data to suggest that maybe flows even sort of spin. There's a vertical variation in where the flows go, and that isn't necessarily well represented by a logarithmic law. And that also, that logarithmic law also says a lot about those boundary layer dynamics, but that suggests that there's a no slip condition, that it's 0 at the bed. But if you have a moving bed, that sort of breaks down a bit. So this is essentially like getting into the weeds of the model. So I think those places can be improved in terms of if you're looking at small scale dynamics, like a sediment transport study for sure, I think would look into that particularly. Yeah.
So do you think like your discrepancies that you have here could be closed quite a bit if you change that representation?
I think for large scale flows like depth average velocity, I think that the depth average isn't getting it. I think if you started looking at the vertical variation of the currents and compare Kara's vertical variations versus the model, you might start to see where in the water column it's breaking down. because depth average isn't getting sort of how the currents might be changing. And in terms of the flood, maybe there's something going on observationally that we're not quite getting. I think when you're looking at a time series comparison of a particular point, like observationally, this is an important area to start looking at the small scale dynamics, particularly boundary layer flow and how that might change. And I think it'd be important to know the sediment in the area, the eelgrass in the area, maybe have a couple instruments out for sure. I think this would be a good observational future study with like a small scale model. One more question, Bill? Yeah. Yeah. Yeah.
So I just wanted to.
You need just for the people in the
So really very cool work, and it will be very helpful for understanding the biology and nutrient cycling and a lot of other aspects of what goes on in the bay. My comment or point would be, though, that release from the sediment is not a net nitrogen loading.
Mm-hmm.
It's possible that there's nitrogen fixation in the sediments. It's actually producing or fixing that reactive nitrogen.
Like from ammonium, you mean?
Well, by microbes that fix nitrogen from and to.
Yeah.
And so it is a release. I mean, the measured release is inorganic nitrogen that was in the sediment and came into the bay. But we have to ask the question, well, where'd that nitrogen come from originally? Mm-hmm. And so unless it was produced in situ, or unless the bay is just eroding away particles and at some point will just be all gone and bare rock because we've used up all the particles, that it's actually coming from somewhere else, is almost
right. So
certainly. So loading, I think, is not quite the right word. It's an internal transformation and a release over a specific
I don't know what the time scale is from where those nutrients came from, right? I don't know if it's days, weeks, months, years. I'm not quite sure. That's like almost like a spatial variability. If you're near rivers, maybe something came from rivers. If you're near an eelgrass bed, maybe you're dead eelgrass from 10 years ago that are now getting sort of have been degraded. So I think that's definitely I understand the loading versus a source just sort of internally cycling. Yeah.
So I think that's an important
point
consideration to keep moving forward as we move forward with this. So that,
but the right terminology.
But this is very helpful in understanding how things are cycling through the bay. So it's very cool.
Tom.
Very good.